Okay, this is the first of several recordings that are going to cover Bayesian mixture distributions. We will begin by talking about mixture distributions in general. We will then talk about how we use mixture distributions to perform flexible density estimation. And then we will also talk about clustering. So, of course, your instructor is Dan, but the notes are, as always, by Ander. And okay, so let's go ahead and get started. What we will do is we are going to talk about mixture models, and to do that, we will initially talk about something called the Dirichlet distribution, and then we will eventually talk about the Wishart distribution. The first application will be non-parametric density estimation, or maybe semi-parametric density estimation. Maybe the best way of saying it would be flexible density estimation. And then we'll talk about clustering. So we want to be able to define a mixture model and explain the situations where they might be used. And we want to be familiar with Dirichlet mixture models. So let's learn about those guys. Okay, this slide says a mixture distribution is a probability distribution that has a weighted average, that is a weighted average of other distributions. And we'll see this on the next couple of slides. Basically, what we're going to do is we're going to put together several different distributions, add them up to get a new flexible distribution. And so each of the individual distributions, I'm probably going to call those the mixture components. They can be any distribution, but oftentimes we use Gaussian, that is normal distributions, because they're easy, familiar, flexible, and they also add nicely. As I've already said, thinking about a mixture distribution allows us a lot of flexibility. And as the slide says, it results in properties and interpretations that are not present in the component distributions. Basically, the idea here really is by mixing a bunch of pretty simple distributions, we can get a very complex distribution. Okay, so this here is a review slide, just to kind of set things up for the coming slides. If we have, what we have is we've got a bunch of random variables. The way I'm going to think about these guys is that they are IID realizations from some unknown distribution. So in statistics, what we often do is we will fit a parametric distribution to the data. So if things are normal, for instance, what we do is we work hard to find what the best mu is that fits the data, what's the best sigma squared that fits the data, and we call that fitted distribution our estimated distribution. Of course, there's nothing magical about normal. We can do it with the Poisson. If we've got a bunch if these x's up here are counts, what we do is we find the lambda, which describes that count data best. And what we're doing is we're assuming that count data arises from a Poisson distribution. Okay, so what is a mixture distribution? Well, a mixture distribution, here we're gonna focus on the particular case where we've got just 2 components. just to make things simple. But what we're going to say is we're going to say that x has a distribution. Of course, remember the squiggle here says is distributed as, and it says pi times f1 plus 1 minus pi times f2, where pi in between 0 and 1 is a weight. This says that the distributions can be any distribution. It says that most commonly the base distributions are the same family. For instance, they're both normal, but there's nothing that says they have to be. It just makes the problem more complicated if we allow our mixture to arise from any number of distributions. But it is possible for them to come from two different families. Now here it says both the weight and the parameters for the base distribution can be estimated from the data. So remember, if you think back to the very first day of class, let's not make that red, let's make that blue. We talked about Mathland, we talked about real world, and our models live over here in Mathland. Our data lives over here in the real world, and what we want to do is we want to take a model from Mathland and fit it into the real world. So statistics really talks about estimation, where we're crossing the bridge between these guys to try and find the parameters. Here's a better way of saying it. We start over here with data. What we do is we cross the bridge over here into Mathland and figure out the model and the parameters that fit it best. Okay? What we're going to do here initially is, rather than talking about estimation right away, we're just going to think of this in Mathland. We're going to think of this as the way we often think about a model is we think about it as a hypothetical way of generating the data. So here is the way a mixture distribution would generate data in Mathland. So if this was the data generating model, this is how the data arose. What we would do is we would flip a coin. That coin has a probability pi of being heads, and that pi, of course, doesn't have to be 50-50. If it's heads, then X is going to come from the first distribution, and if that coin is tails, it's going to come from the second distribution. So you can imagine that generating data from a mixture distribution is a two-step process. Flip the coin to decide which of the two distributions you're going to draw from, then draw from that. And of course, if the coin is not fair, if pi is 0.75, then 75% of the draws are going to come from the first distribution, and 25% of the draws would come from the second distribution. Okay, so here's the picture that I want you to have in your mind. This is our first distribution. This green curve is our first distribution. And then this orange curve is our second distribution. And notice that notice that the area under the curves I have tried to show is very different. So here, pi 1 is bigger than pi 2. Maybe 75% of the data is coming from our green distribution and 25% of the data is coming from our orange distribution. So if we were in that scenario that I just described, where you flip a coin and you decide, and if it's heads, you draw from here, and if it's tails, you draw from here, you can imagine doing this over and over and over again, and what you would get is you would get data that would have two bumps. You'd have a bump that kind of follows the green distribution and a bump that follows the orange distribution. But importantly, so that's what I'm trying to show here with the red curve. Importantly, the red curve is the sum of them. So notice what happens where these two distributions overlap. You've got, if you got a draw that came from here, let me say it this way. You could imagine a draw of this value arising from the green distribution or the orange distribution. It would be a tail, a coin flip that resulted in heads, which means we're drawing from the green distribution, but ended up way in the upper tail. We could also get that value by getting a coin flip that resulted in tails, but ended up in the lower tail of that distribution. And so the sum of the distributions is this red curve, and the red curve, of course, would be the sum of the heights of the orange and the green. So here, in this particular case, it's always the case that pi 1 plus pi 2 has to equal 1. Here, we're going to say that here it's clear that pi 1 is greater than pi 2. And you can ask yourself for a second, why does pi 1 plus pi 2 have to equal 1? Well, we know that a density has to integrate to 1, right? So if I were to integrate this, if this is a perfect probability model without accounting for pi, if I just integrated f, I would get 1. If I just integrated f2, I would get 1. By multiplying this by 0.75, say, and multiplying this by 0.25, I get a new model. This red curve is guaranteed to integrate to 1 so long as the pi's sum up to 1. Okay, so that's our picture for a mixture distribution, which, as we described in Mathland, is going to behave this way. It's just summing a weighted sum of two distributions. We haven't talked about estimation yet. That'll be in the next video. Okay, there's nothing magic about having two distributions. Here is a mixture of k mixture components. What is required is that all of the pi's sum to 1, so the set of points where the pi's sum to 1 is called the k-dimensional simplex. But you can just think if we're in, say, 3 dimensions, if k equals 3, points on the 3-dimensional simplex would be points like 1/3, 1/3, 1/3, a point like 1/2, 1/4, 1/4. Any 3 numbers, they have to, of course, be positive because they're probabilities, but any 3 numbers which sum to 1 would be on the k-dimensional simplex. So it's a pretty simple idea of what that would be. Of course, the point 1/2, 1/2, 1/4 would not be on our k-dimensional simplex. Okay, so this is just trying to illustrate that idea. Here now what we have is we've got 3 components. We're still dealing with 1-dimensional data. I'll show you a picture of 2-dimensional data on the next slide. But here is component 1 is this blue guy. Component 2 is this green guy. Component 3 is this orange guy. And so long as they are valid probability densities in their own right, then if I sum them, if I weight them with weights that sum to 1, then I'm going to get an overall density, which is given by this red curve, which is valid. It's going to be non-negative. It's going to be equal to 1. That's what is required of a density. What you're also hopefully seeing is this, that we can make a very flexible density via a mixture distribution. So one of the things we're going to talk about, one of the statistical goals will be to perform density estimation and look by starting with 3 pretty simple models, we can end up with a density. Our mixture density is pretty darn complex. There's nothing that says our random variables have to be univariate. We can talk about random vectors. So a draw from this, of course, would have an x1 value. It would have an x2 value. Here is a mixture distribution in 2 dimensions, and it has 4 components. I've drawn them basically as Gaussians, but notice the Gaussians have different means because they're centered at different places. They also have different covariance matrices because the ellipses, which describe the individual densities, are different. And then I haven't drawn the overall mixture, but you can imagine basically the overall mixture would almost be like laying a blanket over these four things. You would end up with a surface which has four different modes, four different peaks. And of course, they would sum. So for instance, the saddle, if you will, between these two densities is not going to be too low because we've got some overlap in those densities. Okay, so the hopefully the idea of a mixture distribution is pretty simple. And what you can imagine that if we wrote this distribution down, it would be really easy to draw from it. We would basically need to do something that would allow us to choose between four choices with probabilities pi 1, pi 2, pi 3, pi 4. If pi 3 is drawn and this is the third component, I would then draw a data point from that distribution. If I flipped my four-sided coin or rolled a four-sided die and came up with 2, then I would draw a variable from, say, the black component. Okay, so in math land, it's fine. What we want to do, of course, is do this in statistics land. So let me add another slide in here just to kind of illustrate this. In statistics land, imagine we had data that looked like this. And unfortunately, they're not going to be labeled. So what we're going to have to do is we're going to start with unlabeled data. We're going to have to fit distributions to this. So you could imagine my fit looks something like that. Not only do I have to find the parameters that describe each of these bumps, so if these are Gaussian, each one of these would have a mu vector and a covariance matrix sigma, but we also have to find the pi's. And so so you can imagine that estimating sounds pretty challenging because we've got a lot of parameters, and additionally we have to estimate those probabilities. So that's, in statistics, that's what we're going to do. Okay, so this slide is basically an aside. It's kind of Bayesian geeking out, and the first bullet says the field of Bayesian non-parametrics often uses models with infinite mixture distribution. So the idea you should have is imagine some crazy cloud of points, and what you're going to do is you're going to throw down mixture distributions to model that crazy cloud of points. And how many components in your mixture? Well, you're going to allow that to be infinite. If that sounds pretty weird, I think it should. It should feel pretty weird. There is a way to do this. They talk about a Dirichlet process, and this is basically describing that Dirichlet process. But you can fit this with a Gibbs sampler. We're not going to do that. We're not going to do the infinite case. We're going to restrict ourselves to finite mixture models. But this is just kind of a slide that says, hey, if you want to think about taking this to another level, this is something that is a current very active area of research in statistics. Okay, so Where are we at? We have learned mixture models. We've approached it from the math side as a data generating mechanism. Flip a coin, draw from the distribution that you came up with. We've sort of foreshadowed of what estimation is going to be like, where we have a cloud of points and we want to estimate the mixture. And so what can you use these mixture models for? We've already kind of talked about non-parametric density estimation. That's what we don't know how to perform that estimation, but hopefully we clearly see that as a potential goal. We can also talk about clustering. If I can start with unlabeled data like we did back here, all of these blue points, and then we can fit a mixture to that unlabeled data, suddenly I can talk about the points in terms of, oh, are they associated with the red distribution or the orange distribution or the green distribution? Basically, what we've done is we have defined clusters to describe the points. And interestingly, like a point which is here sort of in that overlap between the red and the green, I don't know if that came from the red or the green, but eventually I can assign a probability that a point in here might be like 50-50 red and green. A point down here might be nearly 100% green. So clustering would take unlabeled points to begin with and assign clusters, and it can even be done probabilistically. We've already seen that mixture models are very, very flexible. And there are some other areas for where cluster modeling can be done. One that we've actually already talked about is variable selection methods. So we talked about the spike and slab prior, and what that did was it assigned a probability of being exactly 0 to our regression model. And what you were able to do was you were able to obtain a posterior estimate of that probability. But that variable selection was really an example of a mixture model. Another example is zero inflated Poisson. So we've talked very briefly, well, not very briefly, but we've mentioned one of the properties of the Poisson distribution is that it forces the mean and the variance to be the same. If our data arises from a Poisson with parameter lambda equals 5, the mean of that data is the mean of that distribution is 5, the variance of that distribution is 5. And sometimes, even if you have count data, the Poisson distribution doesn't fit the data very well because the mean and the variance just doesn't appear to be the same. And so people will fit a negative binomial as an alternative model, or if it just is, if that variance is not does not fit it well because you have too many zeros in your data, then people fit a model called a zero inflated Poisson. And a zero inflated Poisson just assigns a probability of a point mass at 0, and that can also be viewed as a mixture. So mixture models are flexible. We're going to do two cool things. We're going to do non-parametric density estimation. We're going to do clustering, and that is what we will do in videos to come.